All right, so this first one, this is if I want to take and go from Celsius to Fahrenheit. Okay. The second one is if I want to go from Fahrenheit to Celsius. Now, the last one, and there's only one way to get to Kelvin, and that's from Celsius to Kelvin. Okay? So Fahrenheit was a dude, created a scale. Well, we'll talk about it later in the next couple of slides. Celsius was a guy curious about temperature. He created the metric version of what Fahrenheit did, and they're both based it on, well, sort of. They have set points. Celsius just said, look, when water freezes, we'll call that 0. Now, this is based on the concept, right? So if heat is a measurement of kinetic energy in some sort of way, right, there's a relationship between the two. Then when something's frozen, the assumption was that there was very little motion, right? Well, later, Kelvin came along and said, look, my 0 is when there is 0 motion. Turns out that's a very, very, very cold thing. Theoretically, we've never ever seen it. We get pretty close to it. But theoretically, we've never seen absolute 0. So Kelvin's was focused on an absolute 0. Celsius was 0 when the water was frozen. And this guy's 0 doesn't make any sense. It does, but it doesn't. Okay. All right, let's move on. We'll learn more. So you don't have to write this down. But what causes temperature? For a long time, scientists didn't know. In 1827, there was an Irish botanist named Robert Brown, and he noticed something. When he put pollen in a dish to watch it, right, grains floating on water, he saw it moving around in a jerky, irregular way, even though the water was calm. This is called Brownian motion. Okay, so I don't know if I can play this. No, I can't. But nobody knew what was going on for 85 years. Then this guy, Einstein, apparently thinks he knows it all, finally explained Brownian motion and what temperature really is. So this you got to write down. So write this down right here. That's what I want you to write down, just this stuff. Atoms, not Adams with a D, not my name, but atoms, A-T-O-M-S, they make up everything. Everything that has matter in it has an atom in it, including water, and they're constantly moving. Your table is moving. Your chairs are moving. There are molecules that are moving around in the table. Now, they don't move a lot, but they're moving. There's stuff going on. Electrons go around the nucleus, but they're bound in such a way that our eyes can't see that space in between, and we can't see that motion because they can't. It's like something that hovers, right? If something goes a little bit up here and a little bit down here, but it's really far away, you don't really see it. It just seems like it's just kind of there, right? That's kind of what's going on with the molecules in your desk. They're kind of layered in stacks. They move a little bit, but basically everything in the universe is in motion. There's nothing that's standing still, not a single thing. Okay? So what is temperature then? Well, and I do want you to write this down. Moving atoms and molecules have kinetic energy. Kinetic energy is the movement of anything in motion, right? Remember that? Our kinematic equations are what we use when we go to predict the motion of objects. So kinetic energy, and by the way, what is the formula for kinetic energy? You guys know that off the top of the head? KE equals 1/2 times the mass times the velocity squared, right? So we could do this with molecules. This molecule has a mass, whatever it is, and it has a velocity, right? It's moving this way. Therefore, it has kinetic energy. Temperature is the measure of kinetic energy of moving atoms and molecules. I should probably point out that this is a molecule, right? That's H2O. That's kind of what H2O looks like. And you can have a gas, right? Steam. So what happens when you boil water and it turns into steam, the water molecules are literally escaping the liquid. They have so much kinetic energy in them that they can't stay in the water. They leave the water and go in the air. That's what the steam is. It's molecules just leaving the water and going into the air. Now, they're very tiny particles, right? And so they kind of hide themselves in the air and you can't see them. Has anybody in here seen a water molecule with your eyeball? No. You can't see them. So once they escape, you can see steam, but that's a lot of molecules. Once they escape and go into the air molecules in this room are moving. You know how I know? Because there's a temperature, right? What's the clock say on the temperature? 66. It's usually pretty cold in here. What's it say? 64. Jeez. Okay, so there's not as much motion in this classroom. Okay? But if we were to boil some water, the temperature would go up a little bit. The kinetic energy of the water molecules as they enter into the air gets absorbed by the air. That's what rain is. The Earth's atmosphere gets hot, and the oceans and the lakes on the planet, every once in a while, an air molecule escapes. Now they collect in the atmosphere. You see them as clouds. At some point, that kinetic energy that holds the water in the air up in the clouds, it cools off. You ever notice it gets real cold right before it rains? It gets a little colder. That's because there's something going on Earth's atmosphere where there's a cold front coming through, and once it hits those clouds that are in the sky, the water just simply falls out of the sky. Okay? And temperature is just a measurement of that kinetic energy. So then there are 3 different types of scales, and we mentioned them before: Fahrenheit, Celsius, and Kelvin. You don't need to write that down. We wrote it down in the formula, hopefully. You wrote some words there. Okay? Now, this is the important part that I want you to write down. In Fahrenheit, water freezes at 32 degrees and boils at 212. According to his scale, that's a total change of 180 degrees. I don't know if I want to go through the history of why he created the scale that way. Why did he set 0 where he set 0? Blah, 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 blah. Boring. You guys wouldn't listen. I'd start immediately. Probably within 3 seconds, half of you would ignore me. But write this down and make sure you know it. Okay? Celsius said, that's confusing. I just want it to be a total change of 100 degrees. So he set freezing to 0 degrees and boiling to 100. It's the same scale. That's why if you look at the old school thermometers, they have it both on the same. Basically, they fill this. Back in the day, they used to fill this with mercury, but it's usually some sort of liquid that expands. Why does it expand? Because as it gets warmer, the molecules in that liquid get excited and they move more. And so as it gets warmer, the liquid expands. That's how those things work. Okay? Celsius is what they use in the rest of the world. We, however, use the imperial system or the British system. I think, actually, in the UK they use Celsius too. So there's that. So 20 in the Celsius, you should probably write this down. 20 degrees Celsius, that's like your average room temperature. That's a nice, comfortable room temp. I went to the Dominican Republic, and it was in the summertime, which it was a little warm. But we had air conditioning units in our rooms, but they were set to Celsius. I've discovered that I prefer 17 degrees Celsius. It's just a little bit colder. It's probably about 68 degrees, 67 degrees or something like that. You ever notice that, like in the summertime, you want it to be really cold, but then in the wintertime, you want it to be really hot, but it's not the same two temperatures? It's interesting. Anyways, can I move on? All right. So to convert between those, there's a scale factor of 180 to 100. That's where that 9/5 comes from, in 5/9. If you take 180 over 100 and you divide the top and bottom by 20, you get 9/5 or vice versa. And then the plus 32 comes from the fact that one of them has to equal 0 and the other one has to equal 32. So those are the conversion factors. So it says, what should the conversion factor look like? Well, we already wrote down the formula, right? That's where that comes from. So if I know what it is in Celsius, I have to do the conversion. And then remember that 0 here is actually 32 here. So if I plug in 0, 0 times this is a certain number of degrees in Fahrenheit, but I have to add 32. Likewise, there's a similar thing. Then we reciprocate the ratio, and whatever degree we have in Fahrenheit, we subtract the 32 to get it to 0. Right? So if I put 32 in here, 32 minus 32 is 0, and then that's going to give me my 0 degrees Celsius. So that's why they do it that way. You don't need to write that down again. I wrote down the things in the beginning. Okay? So on the Fahrenheit and Celsius scales, is it possible to have temperatures below 0? Yes. Right? We see that here on the Fahrenheit scale. Well, if you plug it in the formula, the answer is yes. Well, how do you get a temperature? Like, how low can it go? Well, I want you to write this down. The lowest you can go is called absolute 0. I want you to write the whole definition down. You should also write down there is 0 kinetic energy. No motion. Okay? So you can't go lower than that. That's why they call it the absolute 0. Well, the absolute 0 is negative 273.15 degrees Celsius. The way that they calculate that is based on kinetic energy, right? So you take a temperature and you measure the heat energy, then you compare it to the motion, the predicted motion or empirical motion. The mass doesn't change. So then you say, well, how does this work mathematically to make, what happens if I make the velocity equal 0 or get really close to 0? And so then you can manipulate the equation. In other words, you're going to have on one side some variation or measurement or formula for heat energy, and you're going to set that equal to the kinetic energy, and then you do some algebra. Remember that the kinetic energy we're going to let the velocity approach zero. So you got to do calculus to do that. You got to take the limit at some point. Because if you plug in zero, the whole thing just equals zero, and that, So by kind of working backward, and I'm over simplifying this, but working backwards from that, that's how you come up with this absolute zero occurs at negative 273 degrees Celsius or negative 459.7 degrees Fahrenheit. Okay. Can I move on to the next slide? Okay. So this is the Kelvin scale. Okay. This is the absolute value or absolute temperature of zero. Okay. So basically what you do is whatever the temperature is in Kelvin, you add 273 degrees to it. Okay. And you guys have written the formula down, but here they put a couple of things in here. This is the temperature that nitrogen boils at 77 K. So nitrogen is liquid at room temperature. Actually, it's a gas at room temperature. So liquid nitrogen freezes stuff. So it's very cold. Water freezes at 230 degrees Kelvin. Our body temperature, which is about 98.6 degrees, is about 310 degrees Kelvin. There's some other stuff. This is how hot the sun is. Yikes. That's pretty hot. Okay. Again, the only thing I need you to write down is this stuff right here. So Celsius is metric, but in physics, we use Kelvin. So if you look at my posters, that first poster over there that says thermal rectifiers, I had to do a bunch of stuff with thermal conductivity, which is a measurement of how easily something transfers heat, right? So your cookware is made out of, like most of your frying pans and stuff are made out of some sort of metal, because metals conduct heat well. If I put a iron skillet on a fire, right, like a campfire or your stove that has, if you have a gas stove, that heat that comes from the fire it's conducted, right, and transfers to the iron pan. The iron skillet actually is very conductive thermally, right? Some things aren't conductive thermally, right? So if I were to put a brick on there, the brick would take a lot longer to heat up. But the nice thing about bricks is that once they heat up, they'll stay warm for quite some time. So little things like that. But anyways, absolute zero is very, very low. Okay, move on. Does everybody have that stuff in the box written down? Okay. This is the formula that you've written down on the first slide. So if you look on that poster, I had to convert all the temperatures. Basically, I measured a bunch of temperatures. And I had to convert them all to Kelvin. So if you look at the graph over there, it tells you what the temperatures were in Kelvin. Okay, that's what we do in science. All right, we're done with our notes. We just got to answer a few questions. The weatherman reports that it's a high of 86 degrees Fahrenheit. How would you record this in SI units? Well, you'd have to take the Fahrenheit and convert it to Celsius, and you have to take the Celsius and convert it to Kelvin. That's the SI unit. So immediately, I know it's not this one. And I know it's not this one. So somebody help me. What's the formula for this? Isn't it 5/9 times Fahrenheit? Oh, nope. I already screwed that one up. I gotta erase this. You guys should be writing this down. You're gonna need this example to help you get your homework done today. Right? So I have my temperature in Fahrenheit minus 32. Did I write the formula down correctly? Somebody double check me. Man, I'm good. All right, so I'm going to say that my Celsius is equal to 5 times 9 times 86 minus 32. And I'm going to do this on my handy dandy calculator real quick just for time's sake. So let's do 86 minus 32 real quick, 54. Then I'm going to multiply that by 5, then divide that by 9. So I get 30 degrees. So this is 30 degrees Celsius. Whoops. What the heck, man? Okay. So then to get Kelvin, I'm just going to take 30 degrees. Well, let me write the formula out for you guys. You just take your temperature, right, in Celsius and add 273 to it. And so 30 plus 273 is the 303, isn't it? If I plug in 30 here. 30 plus 273. Okay. And that's the answer in Kelvin. So that's what you should get. Did everybody write all this down? I'm grading your guys' lab reports, and you guys had to measure temperature, which is not a possible physical result. Yeah, what do you think it is?
Negative 600 Fahrenheit.
Yeah. So remember that absolute value, and I don't know if you picked up on this. Yeah, this is the one. Absolute 0 is 0 degrees Kelvin. Negative 273 degrees Celsius, and then it's like negative 459. Is that what it was? Check in your notes and see what it was. Yeah. So negative 600 is not possible. Okay. Good answer. Everybody write that down? All right, last one, I think. The temperature of a substance is measurement of. The temperature of a substance is a measurement of. You guys just wrote it down. Yes. Kinetic energy of the atoms. And that concludes today's transfer of knowledge.